In this video, I'm going to show the image of why we may still apply single-ended signaling in some SerDes systems. In the why SerDes video, we know the most advantage of a SerDes is a great reduction in the number of wires, and then the small number of wires is the most cost-efficient implementation. Besides applying the SerDes to data transmission, single-ended signaling chosen in a SerDes system can further reduce the number of wires from 2 wires if there were differential signals to 1 wire. The single-ended medium must apply with single-ended signaling through a wire, cable, or any PCB trace during the data transmission. But the single-ended signal must reference to signal ground. Alright, why do we still need single-ended signaling in some SerDes systems? Can you think about the efficient images of the single-ended signaling for 5 seconds? Correct. The first one would be the size. A smaller device size or medium size means the low cost. For example, using single-ended signaling helps resolving a large chip area, package size, and board dimension than differential signaling cases owing to the easy signal routing in a design, even though that's not exactly half size because some needed design overhead in isolation. What's the other design metrics we could apply in terms of the size and speed limitation? Think about the data throughput or bandwidth images for 5 seconds. Right, if the system operation speed is limited by the on-chip circuitry or the off-chip components, for example, packaging, cable, or PCB, we could just double everything in chip areas, pin counts, and all off-chip components dimension of a single-ended signaling SerDes, such that the whole data throughput under the single-ended transmission scheme can be doubled compared to the same size of the differential signaling SerDes. Do you know why the data throughput under a certain area is critical? Bingo! Both bit form bandwidth density and area bandwidth density are more demanding as more data throughput is needed. To meet people's demand, we need to provide more data, but through a smaller device size for several good reasons, such as lightweight, reliability, integration, cost, design challenge, etc. The beauty of the single-ended signaling would provide flexibility for those requirements trade-offs, owing to its half-size requirement of the differential-ended signaling ideally. But what are its limitations? Can you think about its impairment images for 5 seconds? Correct. We can review the single-ended impairments image from the white differential signaling video. The first image is the low crosstalk immunity. The single-ended aggressor will easily interfere with its adjacent single-ended victim, and the corresponding single-ended victim will not have any immunity. For example, the nearby TX transmitted pattern interfere with the TX1's transmitted signal. Therefore, the eye opening at the far end RX1 would degrade and is smaller than the eye while the TX2 is not sending any data. Then, the near-end crosstalk between multiple TX lanes will cause any error data during the unidirectional link transmission easy, even though the channel loss is lossless. Is the near-end crosstalk the worst case you could have? Of course not. Think about your bidirectional link image for 5 seconds. Right, another worst case image of the near-end crosstalk is between an RX lane and its nearby TX lane, which result in a higher bit error rate under bidirectional link transmission and higher channel loss. The impairment image is straightforward in that the interference strength of the nearby TX coupled to the RX does not change, but the RX received eye opening from the far end TX reduced while the channel loss is increased. If we treat the crosstalk as noise and the input signal sent from the far end TX is a signal, the signal to noise ratio SNR degraded, and the bit array will increase afterward. Of course, we must apply the equation to remove the ISI, but the attenuated signal power is something we cannot boost at the RX front end. So, the channel loss or crosstalk dominate the SNR at the RX front end. Please remember the second near-end crosstalk image and bear with me for a moment. What else could be the impairment image of the single-ended signaling? Think about the data switching image for 5 seconds. Great. The second image is a simultaneous switching output noise, which is called SSO. For example, multiple links should have a single VDD supply or ground connected not only at the TX side, but also at the RX side in a unidirectional link. The inductor wire exists inevitably through those on-chip supplies and ground to the off-chip package and PCB trace. As the input of the TX toggled, the switching current may cause a big voltage drop at the inductor of each supply and ground pin. The return ground path between the TX and its far end RX would have a big inductor to cause a tremendous switching ripple. Obviously, the SSO at the supply and ground would degrade the signal integrity at the RX input and result in any error data easy. Unfortunately, this is just one serious impairment in the unidirectional link, like the crosstalk impairment in a bidirectional and high channel loss link. The SSO would have a much huge degradation of the signal integrity. Again, I'm not saying we cannot make a single-ended link work well by mitigating those two serious impairments, but that requires a lot of effort in the innovations and verifications in a SerDes code design. Besides the single-ended development effort, do you have other electrical requirements images to niche the SerDes well? Think about the second near-end crosstalk images for 5 seconds. Bingo! The first electrical requirement of a link is the low channel loss, which must be as low as possible. Then, the SNR will improve from the inherent high signal power. What else could improve the SNR? Yes, we must reduce the noise either from the crosstalk or the SSO. Could you think about your frequency response images for 5 seconds? Correct. Higher frequencies would generate more crosstalk or the SSO. If we can reduce the speed as the second electrical requirement of the single-ended link, we might make our life easier, right? Based on both the low speed and low channel loss, do you have any niche images of a special SerDes? Well, the first niche of the single-ended SerDes is the low and low speed link in the computer and peripheral communications, such as VGA, PCI, keyboard, motherboard, and small computers, system interface hard drives. To be clear, if low speed is low, the insertion loss of a channel will be very low as well. That also explains while all SerDes works well in a single-ended signaling. If low speed is a must, can we increase the data rate to a moderate speed? Yes, you could increase the speed, which is high demand recently. But we must keep the channel loss as little as possible. And the straightforward image is to find a very short reach VSR or an ultra short reach USR, which should provide a very low loss, even though the frequency or speed is moderate in a 5 gigabit per second to 10 gigabit per second range. The most popular niche would be a higher I/O bandwidth density and low symbol rate interface in the memory interface or any die-to-die interface. Since the VSR is a sweet spot in a single-ended SerDes, all standard memory, component and module interfaces have been single-ended for several generations and a long time, except fully buffered DIMM, differential DIMM, critical signals, for example, clock and strobe, and some customer memories, etc. Besides those niches of a single-ended SerDes, what else will mitigate the impairments? Think about the improvement images of the crosstalk and insertion loss for 5 seconds. Great! The first thing would add proper ground or ground shading to increase the isolation between different lanes. Therefore, a ground signal ground pattern and the on-chip bound path and off-chip package through the board attached to the PCB board array. Second, to mitigate SSO, the supply impedance must be as low as possible. We could perform a solid power ground grid on-chip routing and add enough bypass capacitance around it. In addition, the featured BGA package will further reduce the supply impedance compared to other wire-bound packages. But you still need to watch out the return path carefully. Third, to increase the SNR, we can optimize the trace routing trade-off between the insertion loss and crosstalk. For example, reducing the trace width will increase the insertion loss, but the nano width may provide more space between lanes and reduce the crosstalk. On the other hand, increasing the trace width will decrease the insertion loss, but the wire width may provide less space between traces and increase the crosstalk between them. Here is the summarized image of why you may still need single-ended signaling in some SerDes systems. Besides applying the SerDes to data transmission, single-ended signaling chosen in a SerDes system can further reduce the number of wires, from 2 wires if they were differential signals to 1 wire. For example, using single-ended signaling helps result in a less chip area, package size, and board dimension than differential signaling cases owing to its easy signal routing in a design, even though that's not exactly half size because of some needed design overheads in isolations. Both bit form bandwidth density and area bandwidth density are more demanding as more data throughput is needed. So we need to provide more data but through a smaller device size. The beauty of the single-ended signaling will provide flexibility for those requirements trade-off, owing to its half-size requirement of the differential-ended signaling ideally. Even though the crosstalk and simultaneous switched output noise SSO would be the main impairments of a single-ended SerDes, we still can provide niche SerDes either at a low speed or at a moderate speed but near lossless channel. The low speed link is in the computer and peripheral communications, The model SP SerDes with low loss is for die-to-die or memory interface. Lastly, a few workarounds can mitigate the single-ended signaling impairments. First, add proper power or ground shading to increase the isolation between different lanes. Second, minimize the supply impedance as low as possible. Third, optimize the trace width and space trade-off between the insertion nodes and crosstalk to increase the SNR. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.